Okay, thank you very much. So maybe I will just introduce myself very shortly. My name is Łukasz Rudziński. I am seismologist in Institute of Geophysics, Polish Academy of Sciences. I am mostly involved in observational seismology, but mainly focused on mining-induced seismicity and source parametrization. But today I will show you a work which is actually connected with estimation of a large possible magnitude, which can be observed in mining-induced seismicity in a very interesting test site, namely Bogdanka Coal Mine. This work is done together with Professor Andrzej Kijko from Natural Hazard Center, University of Pretoria, South Africa, Dr. Katarzyna Mirek from University of Science and Technology in Kraków, Poland, and our industrial partner, Dawid Mul from Lubelski Węgiel Bogdanka S.A. Okay, so here's the primary aim of this study. So the primary aim is to assess the maximum possible seismic event magnitude for areas affected by mining activity, and more precisely to show how the assessment of the upper limit of mine-related events and max can be improved by adding any additional information. For example, as in our case, on surface deformation or presence of tectonic faults. As I mentioned, we worked on a very interesting test site, namely this Bogdanka Coal Mine. This mine is an underground coal mine located in eastern Poland. This is a mine which excavates the coal from the depth of about 1 kilometer below the surface. It works for around 70 years. But what is interesting, the seismicity here is relatively new. It started some 10 years ago, and it happened that together with the mine, Institute of Geophysics, Polish Academy of Science deployed here in this area a seismic network, which is located on the surface, which was located on the surface. This network consisted of 12 seismometers, 8 seconds geosynchronous, and it operated between late September 2018 and end of 2023. During that time, we recorded and parametrized 2,281 events with magnitude above 0.3. Maximum observed magnitude during that time was 3.2. Actually, it was 2 events with such magnitude. Partially, data are available within our episodes platform. After agreement from the mine, we will update this catalog for the whole period of time of work of this network. The magnitude of completeness for this catalog is 2.1. Concerning tectonics setting in the mine, inside the mine we have a few important faults, and in the vicinity of the mine at the border, actually, there is a regional fault which is called Kock. This regional fault is not active, and in historical time it was never observed seismicity on this fault. But anyway, what we believe is important for us to consider, there are 3 segments which we choose based on knowledge from the mine and based on some plans of excavation during next few years. So one of this segment is segment located on N1 fault, which length of 2.1 kilometer. This segment is important also because here we already observed a strong event, actually the strongest one with magnitude 3.2. And we believe that this segment is already somehow activated, and it can be activated in the future. But also we consider in this study segments located on the Kock fault, with one with Kock A with length almost 3 kilometers and Kock B with length of 7.5 kilometers. It is, let's say, the worst scenario we can consider. What is more, the seismicity here is also somehow related with subsidence observed on the surface. So these ground deformations looks pretty interesting, but it looks like common deformations observed above mining panels. They formed rather for few months, not very fast, like for collapse-like events we found in other two Polish mining regions. But anyway, when you can see on the left picture, SAR picture, you can see that seismicity is very focused on the shape, which is also connected with deformation. On the other hand, this very big, let's say the strongest earthquake with magnitude 3.2, which was observed in the mine, occurred also on the edge of this, or one of such subsidence. So here we believe that this observation very strongly support the idea that subsidences can be used as supports for maximum magnitude estimation. Yes, here was this strong event. So we considered three scenarios now. Once the first scenario considered that mining excavation does not activate the tectonic faults inside the mine, and information on the upper limit of seismic event magnitude provides seismicity. It means observed seismicity and mine surface deformation. And two other scenarios assume that mining excavation activates segments on tectonic fault N1. This is scenario 2. And in scenario 3, we consider Kock A and Kock B segment are activated. The question is how to incorporate information on deformation of tectonics into assessment of mass. So since information on deformation is independent of the seismic event catalog, we believe that Bayesian formalism should be a very good tool. In this case, we consider posterior probability density function, which summarize both information on max coming from seismic event catalog, it means from observation, as well as from parameters obtained from additional information, in our case, deformation and tectonic. Here we have a prior distribution of Mmax, which is obtained from this additional information, like in our case, deformation and tectonics, and likelihood function, which consider seismic event magnitudes taken from catalog. As a final results, we take a maximum posteriori PM. Here you can see prior information on Nmax in the form of a priori distribution obtained from deformation and tectonics, where sigma m is the standard deviation on magnitude determination from deformation and tectonics. Sample likelihood function of magnitude looks like in the middle of the slide, where F here is Gutenberg-Richter probability density function of earthquake magnitude presented below. So unfortunately, the magnitude range in likelihood function depends on unknown and max, and such dependence violates the likelihood function regularity property. So it cannot be used without some modification. And here we propose two procedures: one procedure based on shift of the likelihood function and Gaussian prior, and the second procedure based on the fiducial distribution of M max and Gaussian prior. As a final results, we consider the higher magnitude obtained by one of these procedures. The question now is, how does deformation leak information on magnitude? So here we follow Wu, who showed that relation between strain energy in region with volume V and stored energy exists. Then, since relation between earthquake energy and its magnitude also exists, we have in this way relation between magnitude and volume. And now, if we assume that volume is related to area of the deformation, and assuming that we have circular subsidence with some reduced error, we also can have models which describe the relation between magnitude and area or radius. And now let's go to scenario 1, in which we consider deformation, which is connected with this strong event with magnitude 3.2. We have a circular subsidence with radius 0.6 kilometer, and based on three relations between magnitude and deformation from Japanese scientists Dambara and Genk, we obtain two possible magnitudes connected with this deformation. One is magnitude 4, and for two other models, magnitude 3.8. So we took here average magnitude 3.9 and standard deviation 0.2. In such a case, our pure distribution assumes that maximum pure magnitude is 3.9 with standard deviation 0.2. Maximum observed magnitude from the catalog is 3.2, and we also assume that maximum possible observed magnitude very conservative is equal to 10. And here we have examples of scenario 1. So we have a little bit different results for both procedures, but as a final results, we consider the highest one. So here we have a magnitude 3.5 with error 0.3. Next, let us consider scenario 2, when we have mining excavation, when we assume that mining excavation activates tectonic fault N1 in the mine area. We have to take into account that not an entire length of the fault is breaking during earthquake, and based on the Selemon's and Chang model, we obtain that this breaking length is around 16%, which is in our case around 340 meters. Now we use well-known Wells and Coppersmith model, which connect magnitude and segment length of breaking segment. Here used for all source mechanism, and this model gives us a magnitude 4.5. In such a case, our pure distribution assumes that maximum pure magnitude is 4.5 with 0.2 standard deviation, and maximum observed magnitude is 3.2. As previously this is from catalog, and maximum possible magnitude is 10. In scenario 2, we obtain a result which is magnitude 4.4 for both procedures, and also the standard deviation is 1 magnitude unit, which means that this solution looks very stable. And let us now consider scenario 3. I call them here, call these scenarios here as the worst scenarios. As I said, this Kotsk regional fault is not seismically active, but the excavation will go from the east toward this regional fault in next few years, very close to these two segments. So it is good to look at these two segments just to know what we can expect if this worst scenario can happen. So assuming the same models like before, we obtain predicted magnitude from this model for Kotsk A segment like 4.7. And if we consider a breaking of Kotsk B, our predicted magnitude is 5.2. And for such approach, Kotsk A segment is ready to generate event with magnitude like 4.5 plus minus around 1.3 magnitude unit for both procedure. And for Kotsk B, this is actually the worst scenario which can happen here. In our assumption, of course, estimated magnitude is like 5 for the first procedure and almost 5.2 for the second. So in our final results, we believe that the strongest magnitude, the strongest magnitude here, which can be observed for these scenarios I presented, is almost 5.2, but also the error is quite big, almost 2 magnitude units. And last but not least, we also calculated the mean return period for the strongest earthquake estimated within all scenarios. Here we can see scenario 1 and 2. So for scenario 1, the return period of earthquake with magnitude 3.4 is 3.85 years. And for magnitude 4.3 from scenario 2, it means from this segment which is located inside the mine, mean return period for magnitude 4.3 is almost 76 years. And for the scenario 3, we have a Kotsk A segment where the strongest event considered here is magnitude 4.5 with return period 182 years. And this worst scenario with magnitude 5.1 return period is about 500 years, which is really, let's say, in comparison with life of the mine, maybe not very comparable. And now some short summary. So we worked on the procedure which can support analysis of estimation of maximum magnitude for mining-induced seismicity. But what we believe is very interesting that it can provide information, especially for a region with new seismicity, like in Bogdanka case. Of course, where deeper excavation means later bigger magnitude and maybe also activation of different faults. When we consider activation of faults, we have results like here presented here. So this is magnitude 4.4 for magnitude N1. And for these scenarios which consider Kock A and Kock B segment, we have magnitude like 4.5 for Kock A and for Kock B segment 5.16. In this case, I mean, in case when we consider tectonics, you can see that the error estimation is quite big. Also, we have to know that based on tectonics and future mining work only, we provide here another uncertainty which are connected with some arbitrary provided information from the mining plans, but also from tectonics, which maybe is not very well known as we can expect. So now when we see the scenario 1 and case in which we consider deformation as an additional form of supporting maximum magnitude estimation, we obtain a magnitude 3.5 with lower error. This magnitude looks much more reasonable, and also we have to remember that this estimation is directly connected with some observation, which is done by satellites, INSAR picture, using INSAR picture, but also by other, it can be done by other geodetical measurements. And also when we consider the fact that ground deformations are directly connected with seismic events, for example, with mining collapses, when they are formed just before such earthquakes, and the forming of subsidence stopped immediately after this rock burst or collapse happened. We can strongly support the idea that magnitude is really related to the size of subsidence. It means that behavior of ground response to the mining is important information for magnitude for Mmax estimation, and should be let's say considered by seismologists, engineers who are interested in seismic hazard analysis in such areas like underground mining. Okay, thank you very much for the presentation, and we can start discussion.